Yeah, thank you. And thank you very much for the invitation in the first place. And yeah, I have basically, yeah, 3 lectures ahead of myself. And just to give you a big picture overview, what I'm trying to cover. So today we are starting with semiconductor calorimeters. So the question is, okay, what is a calorimeter? What we are trying to measure with it is, over my entire course, is what we call, what also Paolo mentioned, light dark matter. And yeah, there are different ways to get to that point. And again, today I will start with semiconductor calorimeters. Tomorrow, probably a little bit of this will leak into tomorrow as well, but then tomorrow I will transition into semiconductor charge detectors. And then on my third part, I will transition to light target detectors. And by the end of these 3 lectures, I hope you have an impression of the different approaches that we are going to take in order to search for what we refer to as light dark matter. And also there, similar to Paolo, I'm trying to just make sure we are all on the same page. So there's a little bit of doubling with what you've heard before, but I prefer to double things than to lose any of you. And just a key reminder for the direct detection. In general, it's really any direct interaction with the target material. And so just to make this clear, so very often, currently so far, we are only talking about dark matter particles scattering off the nucleus. But as we are transitioning to light dark matter, you might also want to consider dark matter scattering of electrons. So this will be covered tomorrow. And then depending on how wide you stretch the term of light dark matter, if you're going away from the WIMP-like idea and transition to other particles, bosonic dark matter particles, then you start to also consider other interaction channels that include the absorption of those bosonic particles, or something like Compton scattering and so on. So this is really just to make clear the direct dark matter detection, although this is our standard interaction, that's not the only interaction we can probe. But for this lecture today, so part 1, this is actually the dark matter nucleus scattering, is what I will focus on, and more precisely on the spin-independent part. So really the idea that the dark matter particle scatters coherently off the entire nucleus. And just there also a reminder of basically what you call like the master formula of dark matter spin-independent elastic dark matter nucleus scattering. So in the end, in the experiment, what we want to measure is how often does a dark matter particle scatter off a nucleus, and what energy does it give us? So that's basically the DRDE, so the rate over energy, so the spectral rate. And our detectors, what it will look like is here, we measure the recoil energy, and we measure the rate of each recoil energy. So a lot is going on this plot, and don't worry about the details, but typically we have a lot of backgrounds, and what we want to see is a dark matter spectrum would look like this depending on the mass. So this would be a lighter dark matter particle giving you a smaller maximum recoil energy, and this would be a heavier candidate. And so we are trying, what we are comparing then is our background expectation with a potential dark matter signal in order to see whether we found something. When we see something, then of course we try to interpret. So we are trying to say, okay, what is the dark matter physics behind it? So we want to understand what is the cross-section, the probability for this to happen, and what is the mass of the dark matter particle. So this is why you are seeing normally what we are providing is this parameter space where if you have the cross-section on the y-axis and the dark matter mass on the x-axis. And as long as we don't see anything, we exclude signal regions and say here in this example, you can clearly see if this is the background spectrum, so the black stuff, if dark matter had a cross-section as large as what is shown here, we would have seen it. We haven't, so we can say, okay, at this mass, this is somewhere in the GeV range, and this cross-section, this picture here would be somewhere in this region. And you see this is all colored, so this means we have already probed that area and have not seen it. But it's not only the dark matter theory that is behind it. We also have to take care of the halo kinematics and so on. So that's also something that Paolo briefly mentioned. We have this the sphere, or we have a certain model of the dark matter halo around our galaxy, and in the end, it depends on what kinematics the dark matter particles have that also drive the rate that we are observing and the energy. And then we also need to take into account that we are not scattering off a point-like particle, but an entire nucleus. So also the extension of this nucleus has to be taken into account. And this is typically this part. So this is also the form factor that was mentioned before. So this is nuclear physics, this is astrophysics, and this is the dark matter theory we want to probe. And I'm bringing this up because a key part for the spin-independent dark matter nucleus scattering is that the cross-section here scales with the size of the nucleus, so with A, so the amount of nucleons you have in your nucleus to the squared. This suggests the higher your A is, the larger the probability that you observe something. So this is actually super critical for the spin-independent dark matter nucleus scattering. And this is also suggesting when you check typical target nuclei that we pick, for example, xenon, this is really, really a big nucleus. And this is suggesting if you have this big nucleus, this rate will be, so the cross-section will be getting larger and this rate will be getting large. So this is super beneficial to have this heavy nucleus. And then going back to our parameter space here, the cross-section, the mass again, you will actually see that from the scale of what has been probed so far, the xenon-based experiments, they are really the ones pushing towards a very, very, very low cross-section. So we are here at below 10 to the minus 45 square centimeters. So one of the reasons is this boost factor. And then another reason is also what has been mentioned before, that these detectors can scale up very big. So you can have the more target nuclei you have, also you increase your probability. Now, the point is that, I've just zoomed in before to this parameter space, so just going back, here the 1 GeV to the TeV scale, but that is just what we refer to as the traditional WIMP or the vanilla WIMP. This is the region that was also mentioned before, where we are both in terms of the mass at the weak scale, and then the coupling to the standard model could happen just via standard model particles that we have already. We don't need anything else but the WIMP, and this is also what was referred to as the WIMP miracle, that basically we search for new physics at the weak scale with a weak scale cross-section, and basically some of the extensions of the standard model readily provided such a particle. For example, in SUSY, so the lightest SUSY particle was a good candidate, and this is all in this region here. However, if you widen the picture a little bit and say, okay, maybe, we have excluded interactions with the Z boson already. We are down here in this region, just to be clear, so you see here this yellow region, this is a neutrino background that was also mentioned before. Experimentally, it will be hard to go down in there. The first part, not impossible, but hard. But then also in terms of the scale of detector that we need, it will be, at some point, we reach an experimental limit. But theory is not saying this is the end of the WIMP. So the WIMP, or the WIMP, the class of WIMP models can extend further. So just to be clear, when we are saying, okay, once we are down here, we are done, that's experimentally speaking, not theoretically. But what we have not probed much is if you go further to the left, and the only thing you need in order, so from the theory side, in order to motivate this region, is one extra mediator. So down to this region, again, you are still at a scale where you can live with the mediators that we have. But if you allow the whole extension to the standard model also to include a new mediator, then it is viable to assume that dark matter could be in the region below the 1 GeV scale. And Also, it's not crazy to assume that there's an extra mediator. When you just think of it, we are saying that, okay, basically 85% of all matter that we have is made of dark matter. It's hard to believe when you think of the 15%, there are so many particles that you need. So if you count like the electron, the gluons that you need, the photon that you need, the two quarks that you need, you end up with something like a little bit more than 10 particles that you need just for the 15% of matter. And then assuming that the other 85% just require one additional particle, it's not crazy to think maybe at least a second one is required, another mediator. And so that's why we are saying that, yeah, also this region is actually nicely motivated. And like Paula also mentioned already before, that the term light dark matter is very loosely defined. So it's not super fixed, but also the WIMP, to be fair, is only weakly constrained. And so typically the community is moving towards saying that light dark matter is that parameter space where you need an extra mediator. But again, this is just loosely defined. But when I'm saying light dark matter, I'm referring to the sub-GeV mass region. And again, the idea is really that with an extra mediator, so for example, a dark photon, you could actually have the cross-section, in the end, the cross-section that you need in order to make sense of the relic dark matter expectation that we have from the measurements today. And I just also want to be clear, because this is different from the collider experiments. Collider experiments probe at the vertex level. In direct dark matter experiments, we only probe effective scattering cross-sections. We cannot go down to the mediator level, and we only can tell you, okay, this is the effective scattering rate that we have, and this refers to the effective cross-section. So then when we find something, we can tell the collider people, okay, please check the details. But this is also motivating the complementarity of these different approaches. Now the challenge, the experimental challenge, as we go down to the lighter dark matter masses, is when you have let's say a xenon nucleus which is super heavy, which is nice for the A² boost, so the interaction rate. It's not so nice when you consider the signal that we want to measure. So I'm just drawing here a tiny recoil, because in the end, when you have a small dark matter particle trying to scatter off a huge nucleus, you can just picture you have a ping pong ball hitting a bowling ball and trying to observe the shift of the bowling ball. You barely can see it, or you can't see it at all. And so, yeah, it's really just the kinematics here, the scattering kinematics. And so, in the end, the challenge, really, the experimental challenge is to, when going to this light dark matter region, which is, again, barely probed, that's also the case because we have to change our experiment or our approaches in order to be able to probe that. And so just to put it also on the typical mass beam that we have, so that Paolo mentioned, we have many possible or viable dark matter mass. We have the wide mass range, so down from the 10 to the minus 22 electron volts, so constrained by the de Broglie wavelength of the dark matter particle, assuming that in our isothermal sphere, we must have the wave function of the dark matter be contained within the sphere, otherwise the sphere wouldn't be stable. So this is basically from dwarf galaxies, the bound here on this end. And then if you go all the way up to the Planck scale, you would end up with compound dark matter, so not individual particles anymore, but compound. And basically these 40 to 50 orders of magnitude in between, you can find models that are justified and viable. And then from the experimental side, we are trying to probe this. And also this has been said before, depending on where you are on that beam, you have very different approaches. And one thing, I will focus on is the particle-like detection. And today, this is basically the regime where I will be talking about today, but I will creep into the bosonic part also tomorrow. And just, reminder, the wave detection is also covered by Chiara and Katharina. So that's just basically here around the split on this mass beam, which approach you're going to need. Now, the low mass challenge. I mentioned already, a key challenge is in the end our observable recoil energy. And also, this is now just really the summary of what I said before. Here's the wind mass, here's the cross section. This is the xenon, and also argon to some extent is living in this region. And if you want to probe in this direction, so even lower and lower cross sections, you build your detectors larger and larger to increase the probability of an interaction. If you want to go in this direction, that is the question, okay, how do we get there? And there are different ways that you can do. Either you say, okay, you want to, you have your target nucleus, and now you have this the more and more small recoil energy. Then one way is just to lower your threshold, so the energy at which you can start to see something. So the smaller your threshold energy, the lighter the mass that you can probe. Or you can try to find approaches where you increase recoil energy. So you have a fixed threshold, but you're trying to increase the recoil energy. Or you're saying, okay, let's exploit other interaction channels. So for example, the dark matter electron scattering. I will get to all of these over the course of these 3 lectures. But basically, when you have this set around, first of all, coming back to this picture, we just first need to understand what are basically the key concepts of which you can use in order to get to measure anything really. And I think also Marco has shown this this plot, so that's why I'm picking exactly the same, just to make sure I'm connecting there well to the previous lectures. And the key idea is that you have any kind of material, and so your material is nuclei, and when you have a scattering, you generate different kinds of observables. So it could be that you have light, typically scintillation light, or you ionize, so you get charges that you can collect, or you generate heat. And depending on what you want to measure, you use different materials. And so Marco was living down here, so he was discussing liquid noble gas, TPC, so time projection chambers in a dual phase, so both liquid and gases. This is, in this case here, you have both light and charges. Then Paolo will go more into, and he already started to talk about scintillating crystals. So sodium iodine, for example, is a scintillating crystal, and you can also go one step further and not only measure the scintillation, but also the heat that is deposited in these crystals if you cool them down and have the right sensors. And the wrong direction. And what I want to talk about is in this side of the triangle, so measuring both the heat that is deposited in a super cold detector and the charges. So in this case, for today, the goal is to discuss how we lower the threshold. So that's the goal for the next many slides. And just again, the low threshold that we want to achieve is with semiconductor colorimeters. And just to highlight the key players in that area, so there's Edelweiss using germanium, and just so for the scale that you always have an idea of how large or small the detectors are, I'm giving you always pictures with humans on it. So these are germanium detectors. Supercinium S in its current version is using both germanium and silicon. And in these kinds of the semiconductor colorimeters, one advantage is that they are measuring the entire energy. So again, the goal is to measure heat. And so the heat that is deposited, in the end, that is representing the entire recoil energy. And as opposed to, for example, if you just measure the charges, you first need to ionize, and then you just collect the charges. So there's a delta in the energy. But for the heat, you measure all of it. And with this idea already, you can push towards low energies. The contra is that compared to the noble gas detectors, it's hard to increase the target mass to the same, or you can't to the same scale, because in the end, you have crystals, you need to grow the crystals. And of course, you can say then, okay, then we just, if we can do 10, then we can also do 100 or 1,000. But also keep in mind that you still have individual crystals that you have individually to instrument. That's a different story than just increasing the entire target mass of a monolithic target. And so that's really one of the challenges for these kinds of devices. However, at the low threshold region, we are not yet at a point where we have to scale up tremendously. And Edelweiss, like Paula also said, is not operational anymore. SuperStream S at SnowLab is starting to operate now. But the other thing that is that has presented first results is called Tesseract, and Tesseract has multiple detectors in there, and even towards totally different approach using liquid superfluid helium. Today, since I'm talking about semiconductor calorimeters, I'm only referring to the silicon module that they are using in there. You can see here in the size. So these are the two silicon chips they are using. They are sub-gram scale. So just not the ton scale xenon, but the gram scale silicon. And I'm going to show you that this is still enough in order to probe new parameter space. So as we go to light dark matter, we are not yet in a phase where we are requiring these huge detectors in order to probe new parameter space. No, and like I said, they have their first results. I will come back to that also in the end, but here just to show you the mass region, here's 1 GeV. The blue is the results. So we are well in the sub 100 EV region, but you can also see we are at very high cross section. So I mentioned the xenon regime, we are below 10 to the minus 45. Square centimeter. Here we are around 10 to the minus 30. So it's 15 orders of magnitude higher. That is not yet probed. That's also why small masses are still sufficient. However, with these high cross sections, you need to keep in mind that we have an atmosphere around our Earth, and so also where our detectors are located, and we have the entire Earth. So if the WIMP wind is coming from the opposite, it has to go through the Earth, and so with these high cross sections, there is actually a shielding effect. So the dark matter could also scatter in the atmosphere or the Earth. So in the end, if the cross-section is getting too large, it will be just shielded. And so this is also why now there's also a lower limit up here. And you see not only the upper limit. So the one experiment that I actually want to use in order to explain how we get to these super low dark matter sensitivities is a super CDMS. And you can see here super CDMS, these are, so the dashed lines are just the projections of what is expected to be probed. And here the super CMS projections is still in the few GeV region, but also pushing below the 1 GeV. So in a way, this is also still the intermediate regime, but the whole R&D that went into things like this, so Tesseract, the silicon part of Tesseract is actually a spin-off of super CMS. So basically these bigger detectors have an R&D program that was pushing or providing these new devices that are pushing more and more in this direction. And they are built on the same experimental principle as the super CMS detectors. Now, before going into the experiment itself, the same thing has been mentioned before. So clearly, for if the detectors are measuring long enough, and if they are exposed to the cosmic radiation, the background coming from cosmic radiation will be overwhelming, so we need to go underground. And one thing why I want to say or show you a little bit, so I know that Marco talked a little bit about LNGS, so Gran Sasso Underground Laboratory, and also, he talked about that. But what I want to show you is that basically, you have two ways, typically two types of underground laboratories. So either you go horizontally into a mountain, and then you have all this rock overburden that shields against the cosmic radiation. or you go vertically into a mine, and then you have no mountain, but you still have this huge amount of overburden from the normal rock that is part of the mining. And these are the two classes of underground labs that you have. And there are actually many underground labs over the world with different amount, also different amount of mountain or different amount of mining above. And like I said, LNGS was already discussed by Marco. Where I want to go with you today is Snowlab. And Snowlab is a mine, and it's in Ontario, Canada. And I want to go there for two reasons, because first of all, Super CMS is there, and I just mentioned I want to talk about Super CMS. And the other thing is because I don't know who of you has ever been to an underground lab, except Paolo. And you have? I mean, hello, obviously. Okay. Who has been to a mine? Okay. So that's why, I want to go with you there today, because it's different. So first of all, it's Canada. And here again, this is where Snowlab is at. And you can see, so this is really a mining area. So all of this has nothing to do with science. It's they're mining for nickel ore. And the entire organization is ruled by the miners. We are just accepted there. We are guests. We have to obey the rules. We are allowed here. This is the surface. So this is the outside parking lot. We park our car here. We are allowed, and if you are a permanent scientist here, you can also actually go to this parking lot. But we normally, the shifters, just can go here. And then you are only allowed to walk straight to the surface facility. And for your shift, you need to get to this building here, so you're also only allowed back this path here. And if you go elsewhere, you're expelled. So this is really very strict there. And you go back here, and you go to this this area, and this tower that you're seeing here is the entrance to the shaft into the mine, and the elevator that takes you down is what we call the cage. And then first of all, since you are here in a mine area, you need to dress up with your mine gear. So because in the end, first of all, or maybe I should start a little bit early, when you do your first shift there, you do something like mining 101. So you go to a training mine, so a fake mine, where you learn a little bit about the minimal information about what a mine is, when you hit the rock with a rod, how it sounds, whether the rock is loose or not. So you're really in this scenario where you know you won't work anyway, but you need to learn it. And then once we have this little training, then the other thing you need to know is that you also go on shift with the miners. So the miners dictate when you go underground. The mining shift starts at 6 a.m. And you cannot just say, well, this is a little bit early. Could I take the cage down at 8? No, there's just a cage at 6, and you cannot miss it. So that means when you're, depending on where you're sleeping, you normally get up at around 4:30 in the morning. You go to the surface facility, you dress in your mine gear, then you go over to this area, then you stand in line with the miners, and you tag in, so it's also clear that you are now in the mine. And then you take the cage, and you end up 2 kilometers underground. So we are starting up here, and the cage, so Snowlab is 2 kilometers underground. There's a lot of other drifts in here. So the mining happens on all these levels. There's also one level below Snowlab. When you are there the first time, or let me start differently. When the cage is going right to Snowlab, for 2 kilometers, it takes 3 minutes. So this is fast. So this is really, really fast. You're literally dropping down. Also keep in mind that the cage is open on one side, so it has just 3 walls, and you're just passing by all these different drifts, and it's making you crazy. And you also need to turn a little bit away because the little pebbles are flying in. And when you're there for the first time, you need to tell the cage tender this is your first time, because then he will go gentle and just go carefully to the first drift and ask whether your ears are still fine. Then he does the next level. And when you're then fine, then he drops. And And so this is, yeah, then you're down here at, let's say, 6.5, 6.10. Then you have to walk this drift here. So just, yeah, for completeness, for the scientific part of it, again, we want to reduce the total muon flux. And since there was a question before what the muon flux is, I quickly looked it up. For SNOLAB down here, it's less than 0.3 muons per square meter a day. So the suppression from 1 muon per square centimeter a minute is really strong. So that's the reason why we are doing all this stress. But basically, like I said, at 6.5, 6.10, you're down here. And this is then, when you leave the cage, this is the view that you have. So this is now 1.5 kilometers like this that you have to walk. You have heavy mine boots. You have your self-reliant system. If something is failing you, there are refuge stations along the way. And then, yeah, you walk for 1.5 kilometers. And then in the end, SNOLAB is a clean room area, so it doesn't look like this, but it looks like this. So you have all this nice coating, and so when you transition from this region to this region, you have to first take a shower. You get rid of your mine gear, and you get into clean room stuff. Fortunately, SNOLAB has changed a little bit. When I did my PhD, there was not much privacy in the shower. So it was separated, male, female was separated. But my very first shift, I was just in my first half year as a PhD. I came to SNOLAB. My shift superior, she was also female. I met her for the first time. I was like so small, and she was like this person. And then we were going to down the drift, and she was saying, "Oh well," and now we shower. And she was getting undressed and like butt naked, and I felt like, okay, this is really weird. And so I also undressed and then walked, and then we had a shower, and then we get into our clean room. Gear. So that was, again, this was really intimidating back then. It has changed. Now there is a little privacy. You can undress behind curtains. So they changed, but back then, no. And also my postdoc, I met her like 2 weeks or no, 4 weeks before. She was also female. So it was like, okay, now we know each other. Good. So then you are in SNOLAB, and then you first wait in the kitchen area basically until the lab air has been checked and cleared. So then, your shift starts typically at 6:30, 6:45. Then there's one cage up again in the early afternoon. Normally we don't take that. We take the evening shift, the evening cage, which is at around 4. So 16 p.m. So just keep in mind the day started at 4:30, and then until you're up again, it's 4:30 again. So it's a really long day, and you never down there. You don't see the sun. If you're on shift on winter, you never see the sun. So on those days when you have shift, you go underground before the sun rises, and you are back up again when the sun is already down. So just sometimes the life as an experimentalist is, let's say, interesting. The first times it is really exciting, and sometimes it's a little bit tiring, but the work in the lab is actually amazing because it's really the super fancy facility. And again, it's a clean room area 2 kilometers underground. And what I'm showing you here is actually, by now it's already old. This is what we call CUTE. It's a test facility underground at SNOLAB. This is where Super CMS is being built now. And you see this the circle. This is where basically the Super CMS cryostat is located now. And just to give you a key idea again of the size, so this is the cryostat, and this is cooling down to 15 millikelvin. So this is just room temperature. It's around 300 Kelvin, universe 2.7 Kelvin. So this is 15 millikelvin. This is super, super, super cold. And actually the way to get there, so for all I know, Paolo will try to cover that a little bit to give you an idea of how we actually experimentally get down to these super low temperatures. Because again, this is super impressive. But I will not go down and tell you how it works, but I'm just saying, okay, we need these super cool temperatures. And in this cold environment, Super CMS has towers, and each tower has crystal detectors. So per tower, there are 6 crystal detectors, either silicon or germanium. stacked here, and then there will be 4 towers inside, and each crystal detector is about the size of an ice hockey puck. So they're around the kilogram scale of silicon or germanium, so 1 to 3 kilogram per detector. And then, yeah, again, the hope is that through these silicon or germanium detectors, dark matter is crossing through, and it will kick your nucleus, and you will measure something. And the measure something, this is now the point where I'm telling you why we're cooling down that much in order to measure the tiny recoil that you get in your target material. And so the key idea is, so this is now a schematic of this detector here, and you have a particle coming in, could be dark matter, but really any particle that scatters off a nucleus, and continues further. Especially if it's dark matter, it will just continue further. And now this recoil does 2 things. First of all, it generates phonons, so it's heat, and it generates ionization, so electron and hole pairs. And if you have a bias voltage applied, you will drift the charges to the opposite sides, and you can collect the charges and measure the ionization signal. Now, the question is, what makes experiments like SuperCMS a low threshold experiment? So I mentioned the name of the game today is lowering the threshold. And what we need to look into a little bit more in this is the phonons that I just mentioned, because they're key to the low threshold. Then I said that in the end, phonons are heat, so you need ultra-sensitive temperature sensors. If you want to measure temperature, you need temperature sensors. And then also the way you read out the signal, that has to be super precise in order to get the tiniest temperature changes. So this is the list that I want to cover. And the first one being just very, very briefly phonons. But really, just a single slide, just to make sure, again, we are on the same page. So the key idea of phonons, they are not particles, they are quasi-particles, because they can be described in a particle way, very similar to photons. So photons, we know they appear quantized, and the same idea as phonon is basically the acoustic equivalent to the optical idea of the photon. And the point being is, if you have here your letters, so these are atoms, and you just that atoms they are bounded forces with each other, and we can just picture those forces between the atoms via elastic springs, just to simplify the idea. And then, if someone was pulling up this atom here and let loose, the springs would basically cause an oscillation, and then depending on your lattice, how it's organized, only certain modes are being allowed. And these are basically then our phonons. So in the end, it's lattice vibrations or modes of lattice vibration that we can also describe in a particle picture. And yeah, again, since they are not particles, we are always referring to quasi-particles. But in the end, you can really picture them bouncing around like a particle. And that is also the picture. Again, phonons represent heat, because in the end, we also know that the more heat there is, the more motion, or the other way around, the more motion you have in your lattice, the warmer the whole lattice is. And in the end, what we want to do is really cool this down to almost 0 Kelvin. So again, 50 millikelvin, this is around the temperature where we are. And basically, it's at rest. It's not moving. And if you have now a dark matter particle hitting one of these nuclei, this is the moment where they will introduce these lattice vibrations that we want to pick up. So that is also why we need to be super, super cold, that any of those thermal fluctuations are basically really quiet, and we can't see any tiny recoil of one of these nuclei. So this is basically really the idea of measuring the heat wave that is propagating through our crystal. And this is bringing me to the second part, the ultra-sensitive temperature sensors, because the amount of heat, again, this is super tiny, and so we need to have very sensitive temperature sensors. We cannot just use a mercury sensor and put it on there. And there are different approaches to it, and typically they use quantum effects. So we sometimes also refer to them as quantum devices. And you see there are multiple, and they all the principal idea is that they have some characteristic that scales the temperature. So it could be, and I will come to this tomorrow, the magnetization of the material that changes the temperature. It could be it could be the resonance frequency that changes the temperature. What I want to go to today, and what also Paolo will get back to, are so-called transition edge sensors that that depend on the fact that the resistance of the material can be temperature dependent. And what I want to actually go to is an even longer name, which is quasi-particle trap-assisted electrothermal feedback, TES. That is a mouthful. You don't need to remember it. I just want to give you the idea that this is, another more sophisticated version of our different use of a TES, and we call it QET, where the T and the QET is an abbreviation on itself, so the TES, so the transition edge sensor. And that is this transition and what it is about. I want to briefly point out, and then what actually makes the QET a QET as opposed to just a TS. Yes. Yes. So there's, for example, the delight experiment, and I will talk about this tomorrow. That is using MMCs. Yes. And then there's also another one, Magneto DM, that has started to use them. So yeah, MMCs are also being used. That one I don't know of any experiment. To be fair, so the kits, yes. I don't know magnetic penetration. Do you know of any, Paulo? I don't know of any. No, I would say the typical really are, the most common is the TS, then kits and MMCs, and also superconducting nanowires are getting more and more attention, or getting some attention, let's put it this way. I don't know of any experiment using those. Yes. Sorry, I couldn't hear it. So basically, we are, so in terms of energy, we are in the milli EV range, so that's terahertz, I think roughly, if I'm doing, it should be terahertz phonon. So depending on whether you're still in an athermal range or in a thermal, yeah. Okay, so coming to the TS, so part of the TS is really that it's in a transition, and the transition is referring to between normal conductivity and superconductivity. And just, I want to give you superconductivity in a nutshell, because often we glance over these effects, but a lot in the experiments that we are using, there's a huge amount of physics behind it. We just accept and adopt, but sometimes I think it's actually nice to think about it, what it actually means. And so, again, the key point is for a superconductor, there's some critical temperature below which the resistance drops to zero. And the question is, okay, how can this happen? And what is the picture behind superconductivity that distinguishes it from a normal conductor? And the idea here is that you have, so if you're following BCS theory, that's just the one that yeah, it's one of, I think, the most common, and it's very workable. You have your lattice, and you have your nuclei that are positively charged. And let's just imagine, just look at this one electron here. Ignore this one now. And so the electron is propagating through this lattice. It's negatively charged, they are positively charged, so they are a little bit attracted to the electron. And so this is basically shown here. So they're a little bit attracted. They are, yeah, they are lifted. And now let's say this electron is not here anymore. Now focus on this electron. What this electron is seeing now is an effective, tiny positive field here. So it's drawn towards this field. So this is basically the idea. Okay, if it's drawn there, this is also where the resistance drops, because yeah, it's instead of being like hindered to pass through, it's actually being drawn, or the propagation is supported by this by the positive field. Now, of course, in this picture, the challenge is, well, there is this electron in the way, so how can this electron now be drawn here if this electron is in the way? So the key point, first of all, and this is now the BCS theory, saying that, okay, electrons form a so-called Cooper pair. And for this Cooper pair, the key point is, first of all, for this mechanics here to work, they need to have opposite directions. And they also need to have opposite spin in order to actually form a bosonic quasi-particle together. So the spins, yeah, if they are opposite, they cancel out. We are not caring about half spin anymore, but it's zero. And so you have effectively, you have a bosonic total state that can condensate, and that's actually an important part. It can condensate to a collective coherent wave function. Now the question is, I still have not explained to you how the opposite momentum, how that is being solved. And the point is that this picture is actually wrong in that sense, that they are not so super close together. Instead, now if you have, these are again the nuclei on the, or the atoms on their, the nuclei on their lattice space. And then you can imagine here the two electrons are actually much further away than the lattice distances. They are very far away. And now the trick is that they are not moving towards each other, but they are basically like dancers circulating. And now in time, so when you have these two moving this direction, they have opposite momentum, right? At the same time, since they are following each other on their track, they are also able actually to, so once this has moved there, they're actually still seeing the extra positive field. So that is really the trick behind those Cooper pairs, is that they are rotating and having this opposite momentum, and this way being able to surf on the positive field that was generated by the other electron. And when you go to effective theory and want to describe this basically a little bit in this Feynman picture, then you're saying, okay, these two are actually coupled together with in this case, a virtual phonon. And so they are bound together, and now they are propagating as one collective thing. And when you want to measure basically the current that is propagated this way, it's actually truly having, so it's quantized into twice the elementary charge. So this has been confirmed that at least these two pair idea is working fine. And then this bound here between the two is super weak. So it's in a micro EV scale, the coupling between those two. So if you're getting above the critical temperature, it's just too warm, and you're breaking up this very weak coupling between them. And so basically the critical temperature is this moment when you're dropping below the energy scale at which this coupling is stable. And just, not very surprising, this involved a Nobel Prize. And just to show you what BCS theory stands for, it's really just Bardeen, Cooper, and Schrieffer, so the names behind the model. Now we understand a little bit what superconductivity is. And the key point is that a superconductor has both a normal resistance and the superconductance. And this is what we can now use in an experiment to measure the temperature change. And now In this case, we are between the normal, the normal resistance and the zero resistance, so the superconductivity, and we are in the transition in between, so that's why they are transition edge sensors, because we are on the transition. And now if you look on the y-axis, we have resistance, we have here the temperature, and this is the region where we are crossing the critical temperature. And now if you have your material at the temperature just on this edge here, so for example, for TSs, often what is being used is tungsten. If you have a tiny change in temperature, you have, depending on the slope of this transition, a larger change in resistance. And that is something that we can measure. And so that's the one key idea. And I mentioned so that the QET have one element in there, which is electrothermal feedback. So the electrothermal, so first of all, yeah, right. So what I should say is that basically the temperature change, in the end, what we want to measure is the deposited energy. And the deposited energy, again, it causes lattice vibrations, it causes heat. And so the energy deposition, so the delta E scales, or the other way around, the delta E, T, the change in temperature scales directly with the change in energy. Scaled, actually I come to the heat capacity in a moment, but scaled by the heat capacity. But the electrothermal feedback is actually something, I briefly want to mention, because again, it's part of the QET. The point is when you have the energy deposition increases your temperature, you're going up in resistance. If you're going up in resistance less and you don't change the applied voltage, less current will be flowing. If there's less current through the resistance, there's also less heat involved. So the joule heat that comes just from the current is getting less because there's less current. And this means if there's less heat, it's cooling down again. So basically, this is the electrothermal feedback. So the energy deposition kicks you up here, and then because you have less current, because of the higher resistance, reduces the temperature again, and you fall back a little bit to the operation point. Now the challenge is the resolution on your energy. Of course, you want to have a very high resolution on your energy measurement. Since the energies, or the relation between temperature and energy scales with the heat, with the conductivity, capital C, it also means when you do error propagation, quite naturally, your uncertainty on, so your resolution of the energy scales with the heat capacity. So this is telling you that you actually really, and I'm talking about the heat capacity in this case of your absorber, and this basically tells you you want to use the smaller your system, the smaller the heat capacity. So in the end, you actually want to have a super small volume, and you also want to have a low critical temperature. And the typical dimensions are somewhere in the tens to hundreds of micromillimeter scale. So they're super small. And temperature scales, again, we are in the tens of millikelvin range. So that's why we need those cryostats. And this is just a picture here, an optical picture from a tungsten TS used for near-infrared measurements. Just again, here 50 micrometer scale, just to give you an idea of how tiny these devices are. Now, getting back to dark matter particle measurements, we want to actually have a certain chance to see them. And if you have now these super tiny devices, we will, not in our lifetime be able to see a dark matter particle interact directly with one of with this tiny thing. So we want the opposite. We want something really large. So the question is, what can you do? What are the tricks that you can play? And one key idea is then maybe you don't use like the tungsten itself as your absorber, but actually you decouple your absorber volume, and you attach the TES via weak thermal link to your absorber, and you want to increase that part, and you can basically make it as large as you want to a certain degree, but basically the idea is to decouple those two systems. And one way you can do it is, for example, if you say, okay, this is our absorber now, should be germanium or silicon, and you put a layer of aluminum. So this is now new. Before I was just talking about the tungsten TS, but you also put a layer of aluminum on there. And the key idea here is that the TS is tungsten, and you want to operate at a critical temperature of around the transition edge of the tungsten. At that temperature, where this is in transition, the aluminum is superconducting. And now the key point here is if you have your absorbent, so for super CMS, what they want to measure is only the thermal phonons. So thermal phonons are in thermal equilibrium with everything. You have your energy deposition. You get phonons out of equilibrium, so you have higher energy, so you have the higher energy phonons. And you don't want to wait until they thermalize, but you want actually to collect them while they're still athermal. And the cool thing here is that the athermal phonons, when they reach the superconducting aluminum, they have enough energy. So again, superconductor, I told you about the Cooper pairs, they are loosely bound, but they are bound. And the athermal phonons have just enough energy to break them up. The thermal phonons don't. So basically, this is the moment where you can separate between athermal phonons and the thermal phonons. The athermal phonons have enough to break them. So when you have athermal phonons reaching this area, they will break the superconductors, superconductors, the Cooper pairs, and you split them up into two individual particles. And now you have the layer of tungsten here. And now there's another, it's all, so that's actually also one comment. When you are in experimental physics, you want to do particle physics. I was always intrigued by particle physics. I was not listening so much condensed matter physics when I was doing my studies. Now being in this realm, you have to think about condensed matter physics. Now I start to like it because it makes sense. I know why I'm learning it. But a lot of these, when you're building experiments, you're not just doing this one part of physics, but you really have to open up to other realms. And now, talking about condensed matter physics and superconduction, so if you have a superconducting material and some interface with another material, could be another superconductor, could be other material, these two materials will affect each other. It could be because there's a tiny bit of stress, which when they cool differently, and or you have some other interference between the first few atomic layers. And one way or another, what is happening here is that you basically, so this weak scenario of the superconductivity, to some extent, you reduce the probability here for superconductivity. So in a way, is that differently. Here you have your gap, so the Cooper pair energy gap, so the energy that you need to break the Cooper pair, or the other way around, the binding energy of the Cooper pair. In this, can we close this? I don't know how to. Okay, good. So the gap here in this region gets lower. So they are even more weakly bound, or said the other way around. They will not form Cooper pairs again when they reach here this transition area. So they are falling down this potential. And then if they reach the TS, again the TS is in transition, they won't form Cooper pairs here anymore because we are not in the superconducting state. And basically you are here capturing those broken up Cooper pairs. And so this is basically where so I told you the electrothermal feedback part, this is the quasi-particle trap assistance. So this is the trap assistance that is collecting the quasi-particles. So it's just that, yeah, and in this picture they can also interact here. It's just that we make these aluminum, what we call aluminum films, larger, so that there's a higher probability to actually collect them. So it's also we call them phonon collectors, just to really collect more of them. So.
Related question, so why not just make one giant tungsten fin? Why can't it be as just cover the whole?
Yeah, so in the end, you still want to have, so the tungsten is not in a superconducting part. So in a way, there's leakage into here, but the part that you want to have is actually the separation between thermal and athermal. And so you want to actually make this, if anything, rather small, but this one really large, that only the athermal phonons are getting in there. And again, for this separation, what you need to be at is in the superconducting state. And
the white point at the top, that's the quasi-particle, right? There's no actual aluminum atom.
yeah, exactly. That's basically the broken up Cooper pair. It's not, no aluminum is propagating there. Yeah. Yes. I will come. That's the right question. I'm sorry. Okay, I said this before. I will come to that on the following slides. What we are actually measuring, because right now I've just told you that okay, the athermal phonons somehow they are propagating towards generating those quasi-particles in aluminum, and then they reach the TES. But the question is, what are we actually measuring and how? And so before getting there, I just want to show you where those QETs are. So this is super CMS. So again, the ice hockey puck sized thingy, and you see many tiny dots on top of this detector here, and these tiny dots, each of them is one QET, and there are thousands of QETs on this entire surface for tesseract. So these sub-gram scale silicon devices, you see two arrays. I think in total it's something like 50 QETs, and they are grouped into one channel here and one channel here. For super CMS, they are grouped in 4 channels. No, sorry, 6 channels. Here's 2 channels. There's one QT is one of these dots here basically, and then you align them to have like one collective channel. And now the question is, okay, what are we actually measuring? So this is again the picture that I had before, and normally you require some kind of circuit. So I said before the TS, the key part that we are interested in is the resistance and the change in resistance. And so coming back to this picture, we have the resistance here, we have the temperature here. In the end, the change in energy causes the position of energy causes a change in temperature, causes a change in resistance. And this is here what we call the resistance is the TS. Our T is for the resistance in the tungsten. And then this is the entire circuit that we have. And the key device is this tiny little loop here that is shown in the circuit. And normally you just hear, okay, and then we are measuring this wire squid. Now, coming back to the point when you're doing experiments, you're doing much more than just particle physics. A squid is actually a super fancy device in order to measure tiny differences, in temperature, but they are not measuring a temperature difference. So the question is, okay, what are squid actually measuring? And this is the next part now. Yes. So the bath is in principle provided by the cryostat, that you're permanently cooling down the whole system. So it's just really illustrating that when you have your silicon or germanium, this is this part, then you have your TS with the tungsten and aluminum and so on, this is this part, and the whole thing, the whole device needs to be cooled down and then via the cryostat basically. So this is in a way the heat heat bath is provided by the cryostat. So those these things are basically the heat links, and so you have just because they're interfaced, you have the heat link between the two, but you also have the heat link then to the cryostat in the end. Yeah.
He's just saying there's no separation here between the drawing of the aluminum and the tungsten, right?
Yeah. 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 So coming to the squids. So basically, I'm just going now the opposite scale of devices, because in the end, the key idea of the squid is going along the same way. So it's in the end, a squid is a interferometer and device, but on quantum level. But before going to quantum level, let's just stay with macroscopic systems. And in this case, so this is just a sketch of how the Einstein telescope might look like. And so the whole gravitational wave world is using interferometers. And the key idea, just as a reminder, is that you have a certain light source. Then you have a beam splitter, so your light is partially reflected and partially transmitted. Then you have mirrors, and your light is being reflected again. And then here it's transmitted, reflected, and depending on the phase that is between those two, you have constructive or destructive interference or something in between. And then the idea for the gravitational wave is if you have a gravitational wave passing through here, it will change the length of this arm. And the moment you have a different path length between this arm and this arm, you get an interference pattern. So that's just a key idea of interferometry. And just to give you not only a sketch of what could be, this is just a reminder of how something that exists and has done groundbreaking measurements in terms of seeing actual gravitational waves. This is the scale we are talking about. So this is these interferometers, the same pictures as before, just a little bit more details. And first of all, these are 4-kilometer long arms, so it's really kilometer scale that we have here. And then the other thing is that before actually to further extend the arms and without building longer and longer systems, they mirror the incoming light back and forth and back and forth and back and forth many times to just really make it as long as possible. Just that's kilometer scale devices. The Mach Zehnder interferometer, similar idea. The key difference is that again, similar idea. You have your laser, your incoming light. You have a beam splitter. And then at some point, I will come to that in a moment, you merge the two things again, and then you measure the interference pattern. So the difference here with the Mach Zehnder is that you don't go to the arms multiple times, but it's just really each of those go their way once, and typically this is more tabletop-like. But the key idea is exactly the same. And then what you do is, for example, you're interested in the material properties of something, and that's something you put into the beam here, and then you can measure, for example, the refractive index, because depending on the refractive index and the light that is coming out here will be shifted with respect to an empty cell, for example, here. And so this is really a device where you can do material science and just see, okay, how much of a phase shift can you get? And now the question is, okay, these things are, again, super precise. Is there something similar idea for high precision electrical, or we are coming to that, magnetic measurements? And that's exactly the key idea of a squid, is this interferometry. So here, the picture of a squid. So you're not coming in with a laser, you're coming in with a current. And then, yeah, you're splitting just like the light was split. Current, just Kirchhoff rule, and the current will split itself. It will go left and right of the loop. Then you have something in here which may shift your phase, and then the current comes back together and leaves. So that's just the basic picture, yeah, of what the idea behind the squid is. And just also to give you an idea of the sensitivity of such a device. So in the end, the squid will be a magnetic measurement. So actually, sorry, I should have mentioned this before here. Why the magnetic part? So coming back to this picture here. So when you change within your TS, when you change the resistance, because you have this temperature change, you have a change in resistance. This means here you have a change in the current that goes left and right. So again, Kirchhoff rule, it really depends also on the resistance that you have. And if you change the current, you have here a coil. If you change a current through the coil, you are inducing a magnetic field, and so you are changing of this coil the magnetic flux. And so that magnetic flux here is threading the squid. So in the end, what the squid wants to measure is a change in the magnetic flux. So again, just we have the energy deposition causes a change in temperature, causes a change in resistance, causes a change in current, and the current induces a magnetic flux change. And that is what we want to pick up with the squid. And just to give you an idea of the sensitivity we can achieve with squids, it's 10 to the minus 18 Tesla. And just when you want to know what your magnetic field of your own brain is, it's 10 to the minus 13 Tesla. So it's just really, that's what I mean with super sensitive devices. Now the question is, what makes them actually so sensitive to changes in the magnetic flux? And now there's a couple of cool effects that are coming together. And this is also, I'm showing you this. I know we are diverging from like the particle idea, but always keeping in mind when we want to measure something, there's so much cool physics behind these detectors that we are building. That's something I think worthwhile just looking into the details. And one thing is, I said we need to have something that's causing a phase shift. And this is what we are calling Josephson junction. And the key idea, so first of all, our squid is superconducting. So I told you already, we have those, we have Cooper pairs, so we have what we call supercurrent. So the current is not quantized now into individual electrons, but it's Cooper pairs. And if you have an insulating barrier, there's a certain probability the wave function of your supercurrent or your Cooper pairs spills over across the insulating barrier. So this is just tunneling effect that you in the end, depending on the width of the barrier and also the amount of Cooper pairs that are coming here, you have a certain tunneling probability, and this in the end comes with a phase shift. So this already there, you can already see that, okay, this is the idea of how we get this phase shift in there. And I should also mention that there's something that is a critical current. So the probability, and at some point is only so much that the barrier can, current that can flow through this barrier. So in the end, it's a barrier, right? So same with any barrier. If you have too much current coming up here, it starts to pile up. And when you have current or charges piling up here, you start to acquire a voltage across the junction. So that's something we want to keep in mind. So as long as the current that you send in here is below the critical current, all of the supercurrent can go through with a certain phase shift. And it's good. The moment there's too much current here, you start to acquire a voltage across the junction. And again, also that worth a Nobel Prize just to have this understanding of these junctions, and so that's also why it's called Josephson junction. But yeah, coming back to this point. So one thing we need to keep in mind, I mentioned this superconducting is really necessary for this whole device to work, because again, I said that basically the Cooper pairs condensate and you have this one big condensate or collective wave function. And you cannot just simply have any kind of, so when you stick with the current comes here with a certain sign or oscillating term, and in the end you cannot just ignore the fact that the wave function is extending over the whole area. So the phase difference between the junctions, it has to be an integer multiple of 2 pi. So this is really the quantum mechanical condition for the superconducting state to keep the condensate, to keep the coherence. So this is basically a coherent condition. So in a way, this is the condition that needs to, or the system that the system keeps. Now coming to the moment that we actually have a magnetic flux threading the loop. So the magnetic flux is just the magnetic field times the area. And the magnetic flux, this is actually related or connected to the phase difference and via this term. And so basically this term is telling you that the magnetic flux itself is actually quantized. So again, it must be a multiple integer of 2 pi. So phi, your magnetic flux, is a multiple of the magnetic flux quantum. So again, magnetic flux is quantized. And you have this relation. Now coming back to this whole picture, that only multiples of 2 pi are possible, or the flux is quantized. This basically means if you're looking at the entire loop, you cannot have, this is why it's saying it must be 2 pi. If you just, this is just a picture, an idea of how it is looking. So if you have the wrong delta or the wrong phase difference, then you are not getting this coherent single wave function, single phase, but you are having this mismatch basically in your wave function. This is just physically not possible, and so this is basically just this part here picture that we only have multiples of 2 pi. And in order to get there, what the squid or the whole system is doing in order to keep this condition, so that this is still true, that physics still is working, a current is being induced counteracting basically leveling out the phase difference. And now, if you have this greening current, this goes in the circular direction, and now you have one direction where this current is against the bias current, and this direction where it's together. And what we do with the squids, we operate them with the bias current. We have it such as just so below the critical current. Now, in order to keep this condition, the squid is inducing an extra current, and now these two currents here add up, and now these two currents together are above the critical current, and when we are above the critical current, we start to acquire a voltage. And this is what we can pick up. So the voltage is what we are measuring in the end. So here, this is typically the junction, is how we display them via this crosses. And if there's a voltage growing around this junction, this is something we can measure. And this is really then the trick of this squid, how we do it. And then in the end, what the squid is, so what we are measuring is the voltage, and this is the change in the flux. And again, since the magnetic flux is quantized, we start to acquire a voltage as the current is growing. The more current we have, the more voltage we acquire, until we are getting to the point where we basically are at the quantization limit, and then we drop again because we're losing or because how to say, we have a jump in the passage along the junction, and then we are growing up again until we reach that voltage. So in the end, the squid is really a magnetic flux to voltage converter. And again, so this is the trick that we are playing. We are using these super sensitive magnetic devices in order to get something that's just a voltage that we can easily measure. And just to give you an idea of the size of full super CDMS squid array chips, so there are many squids on there. This is how it would look like. So this is 4.5 millimeters. But again, this is an entire array because you cannot, you can, instead of just operating one squid, you can have many squids. But yeah, just to collect what I've told you, a squid is really a collection of three super cool quantum effects, actually superconductivity, the tunneling effect across the Josephson junction, and the magnetic flux quantization. So it's just, in our circuits, it's just a circle with two crosses, but there's a huge amount of physics behind there that gets us to that point. And just another example of what you can do when you have these devices. You can also just measure. So this is George Washington on a dollar bill. And you can measure the differences of the ink magnetization with these devices. They are picking this up nicely, and you can measure all kinds of cool things with squids. Yes?
Want squids to be as accurate as possible. There's basically direct link between how good they are in signal. In super CDMS and stuff like this, are you actually limited by the sensitivity of the squid, or is it both steady right now?
No, I would say it's not limited by the sensitivity of the squids. It's more really higher order noise that is coming in. So it's true that within when you're looking into the signal that we are collecting, I'm not just talking for super CMS in general. That we are using those squids and TSs or MMCs. The signal that we are collecting is a time series, and when you translate this into frequency space, this is basically where we are trying to see the noise level. This is where you can also see some squid noise, but the dominating part, at least for super CMS, is not the squids. Yeah. So, but coming actually back to super CMS, so after this little diversion from the particle detectors, so putting this all together, you have here, you have the squids. They are tied, so they are lined up here on this what is called vertical flex cable. So it's really you have those squids on cables, and those cables attach here to the side of the tower, and they are connected in the end by here the electronics to the TSs or the QETs. And then this is a picture of how the QETs actually look within super CMS. So you have here the tungsten, or the tungsten aluminum overlap region, and then you have these huge aluminum fins, and then in the end you get to the squid. So that's just now putting it all together, how it looks for super CMS, and then coming back again to this thermal pictures. So that's what I was mentioning. We can really picture them as quasi-particles, because in the end you have here your random particle interaction site. So you have some energy deposition, and you have this lattice vibration that propagate around just like ballistic particles. So they go, there's a certain probability for them to reflect, so they scatter around. And they have a high probability to being absorbed when they reach the aluminum fins, where again they have enough energy to actually go in there and break up the Cooper pairs. So basically that is the picture that you have, that they scatter around until you reach one of your sensors. I mean, clearly, real world, there are losses, so not all of them are collected eventually, but first order, in an ideal world, they would scatter everywhere that is not having an aluminum area, and they're just collected where we have aluminum. And then, yes? So let's say, yeah, critical size is a good question because there's a multi-layered answer to it. It always depends what is the more helping and what is making it worse. So if you have, and you see here the attempt was really to have as much coverage as possible. No, the one thing is that first of all, you need to have space still for the actual, let's say, electronics to propagate, and then you also have the instruments that are actually doing these things, and then yeah, it's I would say at the stage of super CMS, it is really in the end a processing, a fabrication limitation. So yeah, that is, and in the end, so also I mean here for the collection, you don't want to just have like one big layer of aluminum because you have losses. You always need to see, okay, how large can it be that you still have a lot of collection, because in the end, like I said, this process here from the aluminum fin to this interface, this is by diffusion, and that's also a time scale question then, but you have until they reach here, you have losses, and so if these are getting too large compared to the TS part itself, yeah, you just recombination happens and you're before they reach this interface, and you lose the signal. So there's a certain kind of optimization between collection efficiency from here to here, and between collection efficiency from here to here, and you can simulate or calculate those. That's I would say where you optimize. But yes, that's basically the one answer to your question is here the size limiting part is the collection efficiency of the quasi-particles, and the limiting factor here was in the end really how to fabricate it in the end. That said, we also it also depends in the end whether the fact that you have those interfaces has side effects that you don't like. So there's actually something that we start to see that maybe those interfaces are causing side effects like extra stress in our crystals that we then starting to see as phonon-like signals, even though they are not. So this is something, where there might be further limitations that we are just starting to see because this is the first time these things are operated in this regime. Yeah.
Graph is ballistic.
Yeah, and this is just really a sketch. It's just a draft, a drawing. It's sorry, it's not like the draft. But yeah, it's just really. Maybe I should call this drawing. It's really just a sketch. Sorry. Yes. Yeah. Perfect. And so then, what we are seeing in the end, what I mentioned before, in the end, what we are measuring is the voltage over time, and or the current, depending on how you read out your squid. And in the end, so if there's no particle, no deposition here, you will just have, so the width of this is just really noise. And there was a question, so squid noise, adds this TS noise, Johnson noise, so just from intrinsic heat, etc. So in the width of this, there's multiple components. Now, if you have a particle interaction here, and you have now phonons propagating to the crystal, so initially, so you have those phonons that hit your sensors right away because they are going straight and they are here. And so this is the first part is really all those phonons that are going straight, and then those that need to first scatter around until they are reaching here. It takes longer, so this is in the direction of time. So after the first direct hits, you start to collect over time all the remaining phonons that are scattering around until you have all of them. So basically, what this part is telling you, and the scheme is giving you position information, because you can imagine that if you have say certain groupings of these TSs, so say these are here, this side is this one channel, then you will see on this side there are more direct hits, so you have a very steep rise than if you're going down here and looking at these TSs until the first atom phonons reach here. There's a little bit longer time, and so your rising part will be a little bit slower. So just from the rising part, of these here, you can have a sense of where in this detector the event was happening. And then the rest of the part is really just a measure of the energy. So until you have all our thermal phonons collected, the integral of this pulse is giving you the entire heat information. And yeah, what about the charges? So since I'm coming to the end now, I've only talked about the heat being collected, but I also mentioned these are actually semiconductors, and you actually also get a charge signal, and you can either measure them directly, so just collect the charges, or you can use them to enhance the phonon signal. And I just want to very briefly point out why we would want to maybe use them directly. And so the key point for that is also like the idea with the noble gas, TPCs, and any direct dark matter detector. If you have a nuclear recoil or an electron recoil, the amount of ionization that you generate per total energy is different. For an electron recoil, you have much more ionization per total energy compared to the nuclear recoil. The phonon signal is basically your entire energy, and then in relation to that, if you have electron recoils, the ionization, so the amount of charge is higher for the same phonon signal. And then when we know, okay, this is the area where there should be dark matter, we can ignore all those backgrounds, so especially all the radioactivity that is around, Compton scattering, absorption, and so on. They would be lying in the electron recoil band. We can just discriminate against and just say, okay, anything in here, this is the region of interest for dark matter. And this is what Super CMS is using in their so-called IZIP detectors. It's interleaved Z sensitive. So I told you that we can, or they can distinguish between the position. Interleaved phonon detectors. So there's, you see here in a zoom in, this is a little bit different from the detector that I showed you before. So here you have the phonon, the QETs, and here you have just really the electrodes collecting the charges. And what about the charges? I think this is something, since I'm now at the end of my lecture, where I want to get back to tomorrow, just to shortly show you the two detectors side by side. So here you only have phonon sensors, and I will show you tomorrow why that makes sense. Here you have both types of sensors. You collect the charges and the phonons. And then putting this all together, you have these two types of detectors. You stack them all up in your detector. And so what Super CMS is doing, they have both IZIP detectors, high voltage detectors, silicon and germaniums mixed. So it's the orange is always the germanium, the bluish is silicon. And in the end, and this is my concluding slide, with these different versions of the detectors. So when you see the Super CMS projections, it's actually 4 different projections behind them for the individual detectors. And the reason you say, okay, you might ask a question, okay, why using the IZIP detectors in the first place? Because they don't seem to have a good sensitivity. But those are the ones that can discriminate electron recoils, nuclear recoils. And each of these high voltage detectors that have a much higher sensitivity because they have this much better coverage of QETs, they require the IZIP detectors to measure the background, and then in the likelihood to constrain the background. So if you will, this is just, you could say these are background measurement detectors, and these are really the dark matter sensitive detectors. And with this, I would want to end, and thank you for your attention.
Stand for again, sorry.
So it's interleave, Z-sensitive ionization and phonon detector. So it's the interleaved is basically showing you that it's interleaved. You have the charge and the phonon, and then the Z dependence was what I was explaining on this picture, that we have a sense of where in the detector it is, and then you have the ionization and the phonon. So it's just all of it together in one thing. Yes. So sorry, second. Hmm. Hmm. But when you use once, you're asking if we have a signal, for example, we tell the accelerator people where to probe, whether they could go lower in cross section. I would phrase it around. At the moment anyone sees something, we will build machines that will be able to go lower in cross section. So once we know we can optimize the regimes. The problem with the accelerators a little bit is that they are highly model dependent. It's not a single answer to that question. So my answer would be it depends on what mediator they are basically, and how the mediator mass relates to the dark matter mass. And so it's really depends. The answer to the question really depends on the specific model they are looking at. Yeah. So yeah, if for the spin dependent, so for these detectors, it's not great. So there is a net spin. So in the end, what you need for the spin dependent is you need to have a net spin of your nucleus, and so the germanium silicon detectors are not the greatest for that. There is a net spin, but it's small, and so overall. Yeah, there was many years ago, there was one paper that also looked into the spin dependent sensitivity of super CMS. Again, it's there, but it's not at the same level of the cross section, because yeah, again, the net spin is small, and you would rather look for either isotopes, or typically you even have like compound a system where you have effectively a higher net spin. So yeah, it would be notably weaker than that. Yes. Yeah. Yeah. Hmm. So I mean, yeah, for the dark matter, it really. So first of all, you in the end you get a block, because you have like four towers next to each other. You get a block, but in the end, I mean, it really depends a little bit from which direction the dark matter is coming. But so I mean, I think how you organize the detectors doesn't really change much. Yeah, but so the thing is that you need to imagine how the dark matter particle wind is coming, and so what in terms of those individuals. So you just want to know, okay, what is my amount of absorber material that the dark matter is seeing, and so let's say you had just really the dark matter WIM coming all straight from the top, which is not the case, but if it was just all coming from the top, then you would say that then maybe you should just have a long tower. But again, this is not the logic behind here. So it's in the end, since we are rotating, the direction of the dark matter actually changes also all the time. So you wouldn't really, you can't really optimize to just one. It's different for detectors where you really have the stream of particles always in the same direction for the LHC. So since you were saying rapidity, pseudo rapidity, there you always have the beams are colliding. You have always the same kinematics in the same directions. This is not true for dark matter. So the direction is varying over the year, and so there's no sense in trying to like optimize in one direction. So you basically just want to make sure you have as much volume as possible. And then the geometry is rather telling you how you build your detector in order to the signal that you collect. That is a bigger question for these detectors. How do you best form the geometry that you collect the signal most efficiently? So, yeah, that's good. Yes. Yes. So basically, let me get back to this slide here. So we can only discriminate against them if you're both collecting the charges that are being produced and the heat. So first of all, what I told you most of the lecture is how we collect the phonons, and the phonons is the total energy. And so if you only measure the phonons, we cannot distinguish between electron recoil and nuclear recoil. We just see the total heat that has been or total energy that has been deposited in the form of heat. So if you don't collect the charges, we can't discriminate. It looks just like energy to heat. If you have also charge collectors or electrodes that collect your charges, you have a field applied that propagates the charges, then if you have a certain energy deposition into, let's say, 1 kV of energy, your recoil is 1 kV. 1 kV in an electron recoil will generate much more ionization per the 1 kV compared to a nuclear recoil. With a nuclear recoil, you just get a tiny bit of ionization out for the same 1 kV. And so if you say this is the 1 kV and we are measuring in the super CDMS and other experiments, so also CREST, we are measuring not only the phonon signal, but so for CREST it will be scintillation, not ionization, but the idea is the same. We measure the phonon signal, that is the baseline, and then we compare it to the ionization signal. And if at a given ionization, the given phonon signal, the ionization is high, we know it's electron recoil. If it's low, we know it's nuclear recoil. And so that's how we discriminate. Yes.
I think we've got more questions. Maybe let's let people go for lunch and ask questions.
Yeah, I will stay here. You can have. Thank you.